This is important stuff. One of your 8-11, one of your exam questions comes right off of this, just to give you an idea of what kind of question you'll be having. But so take a look at this. There will be something like this. It will not be one of the essays, but there will be something like this first type of thing where you have to look at a series of reactions and either determine what an unknown metal is or put the metals in the correct order of the activity series. So you'll have something like this right here. What you said? I want to go back. Any question on this one? On like 1 and 2? Any questions on 1 and 2? We're good there? What about 3, 4, and 5? 3, 4, and 5. You feel confident that you know how to do these? How about that? What about 6 or 7? Halogen replacing a halogen. Really, there's 4 types of single displacement or single replacement reactions. Active metal replacing a less active metal. That's like 1 through 5. Metals replacing metals on most of those. Then there's metals replacing the hydrogen ion. So when you have an acid in solution, the hydrogen ion breaks off. And if you drop an active metal in there, that metal can force hydrogen to take its electron, or really the metal loses its electron so easy that the H plus bumps into it and ends up with the electron. And then the 2 H's join up and form hydrogen gas. A third type is the extremely reactive metals, that when you drop them in water, that extremely reactive metal actually replaces hydrogen on a water molecule. On those reactions, that's the extremely reactive metals, where we have a water molecule. And the water molecule has hydrogen on it. Obviously, a water molecule is really like hydrogen hydroxide. And when you have a very, very active metal, that metal can come in and force the hydrogen off a water molecule. So the H breaks off a water molecule and leaves its electron on there. So like here's hydrogen's electron. It's on the water molecule. And whose electron does the hydrogen that breaks off actually end up with? The active metal. So that active metal will end up giving its electron to hydrogen. So this hydrogen atom will join up with another hydrogen atom from another water molecule that was displaced, and that hydrogen will go out of solution. Really, though, some people look at it not so much that the active metal's forcing hydrogen off of a water molecule, but water molecules in the water that you drink in a water bottle right now, in the water that I used to make this coffee. Water will actually break up in a very small amount into this. So when you drink water, that H2O separates into H plus and OH minus. Water can act like an acid, and an H plus breaks off water. However, it is neutral. You're like, well, if I'm drinking H plus, I'm drinking an acid. That's going to burn my stomach. No. There's an H plus here, yes? But what neutralizes the H plus? This is an acidic hydrogen that broke off. But what else is in there when water breaks apart? Hydroxide ion, which is a base. So if you have an even number of H pluses, if your OH minuses equal your H pluses, the solution's neutral. So there are H pluses floating around. So when you drop that active metal in water, really, it's the H plus that's taking, you're losing the H pluses out of that solution when the metal forces the H plus to take the electron. And then we're left with the OH minuses. So when you drop an active metal in water, it ends up making that water a base. You have OH minuses floating around in there. What are the active metals, by the way? We're talking about these active metals that can force hydrogen out of the solution. Have you looked at this thing? Do you understand how to read this? This is our activity series that we've been looking at. What are the metals that can force hydrogen, H pluses, out of water, leaving behind the OH minuses? Can displace H2 from water, liquid water. Now you're like, but where's the H pluses? It doesn't say H pluses. Well, the H pluses end up with the electrons and the H's join up to form hydrogen gas. So the ones that can actually do that are these metals right here in this top group. If you drop any of those metals in water, we end up with OH minus left and we make hydrogen gas out of there. That reaction would look something like this. Yes? Li plus H2O, we would end up with LiOH and what? Hydrogen gas. But that's not balanced. We would need two of these, wouldn't we? Wouldn't you? Or not? Yes? And what would we need? Two of these, yes? And two of those. Because that gives us 2 times 2 is 4, 2 times 2 is 2, plus 2 is 4. There's my 2 oxygens, 2 in front. There's my 2 lithiums. You'd have to balance that one. Well, anyway, we didn't even have any questions on that. But we've been air testing for 2 days, and I've had no students in here to talk chemistry with. So sorry. How about here? What about 8 or 9? What about number 8? Or 9? Questions? You thought this was very easy. I hope that you don't go straight to the key and copy the answers down. The key is there to look at and to help you through these. What about 10 or 11? Yes.
I'm still kind of confused on illustrating displacement reaction.
Right here?
Yes.
Yes. Is this not the essay, one of the essay questions on the exam? Yes. You will do one of those 4 drawings that were in the 8-10 notes. This is the drawing of a metal replacing a metal. So we have to look at our equation that we had up there. This is our initial equation. That is the chemical equation. Yes? Then they wanted us to write the ionic equation. What's the ionic equation mean? Ionic means write it so that the ions are represented. So NiCl2 aqueous. They write the NiCl2 together in a chemical equation, but they're not together, people. Who broke them up? It's written this way in a chemical equation, but who broke them up? See the aqueous? Who broke them up? Water pulled them apart. The Ni was pulled off by the water, and the Cl's were pulled off by the water. Aqueous means they are not together. They've been pulled apart. There's that. There's that. It's not Cl2 minus floating around in water. It's 2 Cl's. It's only Cl2 when they have joined up to form a molecule. This is not a molecule. They're pulled apart. The 2 Cl2s are pulled apart into 2 Cl's. Now, this is the ionic equation. It's not the net ionic, because who didn't change in this equation? This is part of the drawing. You like said, can you go over the drawing? This is where the drawing comes from. Who didn't change here? The net means only show the one that changed. Who didn't change? Do I have 2Cl minus here? And when the reaction's over, what do I have? 2Cl minus. The net ionic says pull the ones out that didn't change. So the real reaction here is we start with magnesium metal and we end up with the magnesium ion. We started with the nickel 2 ion and we ended up with nickel 2 metal. So nickel went from being charged to not being charged. Why? Magnesium must have forced, if it went from 2 plus to neutral, magnesium must have forced the 2 electrons it has on it. That's what happened there in this reaction. So how do we draw that? So really, what was happening in our ionic equation? In our ionic equation, what was really happening is we had magnesium metal. And we dropped it in a solution containing the nickel ion. And when we were done, we had the magnesium ion. And we had nickel metal solid precipitating out of solution. So we started with magnesium metal. There it is. We dropped it into a solution containing the nickel ion and 2 chloride ions. What happened? Magnesium went from neutral to 2 plus. How did it do it? It got rid of 2 electrons. Is magnesium in family Roman 2? That's not the right color to highlight it in. You're trying to highlight it. Where do I get that magnesium has those 2 electrons? It's family Roman 2. Group 2. The alkaline earth metals, they have 2. Who did they give the 2 electrons? Well, nickel was 2 plus. Now it's neutral. How do you go from 2 plus to neutral? You took 2 electrons. So magnesium ended up losing its electrons to nickel. Why? Nickel 2 plus bumps into the magnesium atom. Magnesium atom doesn't hold its electrons very well. So the 2 plus nickel ends up with the electrons. Active metals get rid of their electrons easily. So now nickel has the 2 electrons. Do you see that? It's not charged anymore. If nickel's not charged anymore, can water hold it in solution? How does water grab and hold these things in solution? Water, what? It has partial charges. I heard someone say partial charges. Correct. I heard somebody say it's polar. Correct. You're both saying the same thing. Magnesium is now charged. So the oxygen on a water molecule can hold on to it. The oxygen's partial negative. Who's holding these in solution? The hydrogens are partial positive on a water molecule. They hold it into solution. Nickel no longer has a charge to be held in solution. Water's trying to grab onto the nickel, but there's no charge on it. It precipitates out. Precipitates right out of solution. Bye. That's what happens in the reaction. What did the chlorides do? What did the chlorides do? Nothing. They sat and watched it happen. They're spectators. They just watched it. Why is there a green dot on the chlorides? That's where nickel's electrons went, right? That's how nickel got to be 2 plus. So when we drop magnesium in, it just gives nickel its electrons, and now it's in solution. Does that help understand what's going on in that drawing?
Yeah.
I don't know if it does. How about 12 through 14? That was questions from the demonstrations we watched. What about question 15 or 16? I'm happy to go over any of those, 15 or 16. If you have questions, ask. Don't be afraid to ask. Today, we now move on to another reaction type that we want to look at more in depth. And those are the double displacement reactions, also called net ion exchange, because this is the one where we have compound like A, B, and we put it with another compound, C, D, and they must be in solution. They must be in solution. And what happens? Well, in solution, it means it pulls apart into the ions. So we would have like A plus floating around. We might have B minus now floating around. This says aqueous, so we would have a C plus floating around and a D minus floating around. That's what it means when they're in solution. That's what aqueous means. What happens in these reactions? Well, we have C plus floating around and it bumps into B minus perhaps. For the reaction to occur, one of three things must result when C bumps into B. One of the things that might happen is when C bumps into B, they are ions. And when C bumps into B, they grab onto each other so tightly in the solution that water can't pull them apart. That can happen. What happens when they bump into each other in solution and water can't pull them apart? They would precipitate out of solution. So one of the three things that happens when a double displacement reaction occurs is something joins up, precipitates out of solution, and water can't hold it. Another thing that can happen is like maybe when C bumps into B or A bumps into D. It doesn't matter. Maybe when A bumps into D, it forms a gas. So they start out as ions, but when they bump into each other, they form a gas that bubbles out of solution. That can happen. Or sometimes when A bumps into D or B bumps into C, they form a compound that is unstable. And that compound breaks down into a gas and water. So the double displacement reaction might form a union, a compound that's unstable. And a gas comes out of it and water comes out of it. So one thing can happen, precipitant forms. Another thing happens, you form a compound that's unstable and it turns into a gas and water. The gas leaves the solution. It's not there anymore. The water becomes part of the solution. What's the third thing that can happen? What's the third type of double displacement reaction that produces a water and salt? What do we call double displacement reactions that form a water and salt as the product? Thank you. Outstanding work today. That's an acid-base neutralization reaction. All double displacement reactions will either form a precipitant, they'll form a molecule that's unstable that goes into a gas, or they form a gas directly, or it's an acid-base reaction where one of the compounds that you produce is actually the solution, water. Today, we're going to look more closely at double displacement reactions. We have videos, 8-what? 8-12 videos. Tomorrow, we're going to do practice problems. That's 8-13. Monday, lab on double displacement reactions, 8-14. We'll do a lab where we take a look at the various types. Good luck with those assignments.